sklearn, model selection, cross-validate. Description. The cross-validate function in scikit-learn is a powerful tool for evaluating the performance of machine learning models. It performs a cross-validation scheme, splitting the data into multiple fold subsets, training the model on a portion of the data, and evaluating it on the remaining portion. This process is repeated for each fold, providing a more robust and reliable estimate of the model's performance than simply using a single train test split. Inputs. Estimator an instance of the machine learning model you want to evaluate, e.g., logistic regression, random forest classifier, etc. X the feature matrix data containing your independent variables. Y the target vector labels containing the dependent variable you are trying to predict. Groups optional group labels for the data, useful for preserving the structure of the data during splitting. Scoring optional a string or list of strings specifying the metrics you want to use for evaluation. Common metrics include accuracy, precision, recall, F1, ROCOC, R2, Negmian squared error, etc. You can also use custom scoring functions. CV optional the cross-validation strategy to use. Common options include an integer specifying the number of folds, a CV splitter object e.g., k-fold, stratified k-fold, shuffle split, etc., an iterable yielding train. Test splits as arrays of indices. None default uses a 5-fold cross-validation. N-jobs optional the number of jobs to run in parallel, e.g., -1 for using all available cores. Verbose optional controls the verbosity of the output during training. Fit params optional a dictionary of parameters to pass to the fit method of the estimator. Predispatch optional controls the number of jobs that are dispatched to the workers before starting any job. Return train score optional whether to compute the scores on the training set as well as on pay test set. Return estimator optional whether to return the fitted estimator for each fold. Error score optional specifies the value to return when an error occurs during fitting. Outputs. The cross-validate function returns a dictionary containing the evaluation scores for each fold. Fit time array the time taken to fit each fold. Score time array the time taken to evaluate each fold. Test score array the scores on the test set for each fold. Train score array the scores on the training set for each fold if return train score true. Estimator list a list of fitted estimators for each fold if return estimator true. Steps. Split the data into folds according to the specified cross-validation strategy. For each fold, train the model on the training data. Evaluate the model on the test data using the specified scoring metrics. Return the scores and other information in a dictionary. Metrics. Classification metrics. Accuracy the proportion of correctly classified instances. Precision the proportion of correctly predicted positive instances out of all instances predicted as positive. Recall the proportion of correctly predicted positive instances out of all actual positive instances. F1 score the harmonic mean of precision and recall, providing a balanced measure. AUC area under the ROC curve measures the ability of the model to distinguish between classes. Log loss measures the prediction accuracy of a probabilistic classifier. Regression metrics. Mean squared error MSE measures the average squared difference between predicted and actual values. Root mean squared error RMSE the square root of MSE, providing a more interpretable metric. R squared measures the proportion of variance in the target variable that is explained by pay model. Mean absolute error may measures the average absolute difference between predicted and actual values. Visualization plots. Classification. Confusion matrix visualizes the classification results, showing the number of true positives, true negatives, false positives, and false negatives. ROC curve plots the true positive rate against the false positive rate, showing the trade-off between sensitivity and specificity. Precision recall curve plots precision against recall, showing the trade-off between precision and recall. Regression. Residual plot plots the difference between predicted and actual values against the predicted values, helping to identify patterns in the errors. Scatter plot of predicted vs. actual values shows the relationship between predicted and actual values, highlighting any systematic biases or outliers. Fine-tune parameters. Regularization strength C adjusts the strength of the regularization penalty, helping to prevent overfitting. Number of trees estimators for ensemble methods like random forests increases the number of trees to potentially improve performance but can lead to longer training times. Maximum depth of trees. Max depth controls the complexity of individual trees, preventing overfitting. Learning rate for gradient-based algorithms adjusts the step size taken during optimization. Number of features. Max features for tree-based methods controls the number of features considered at each split. Uncertainty methods. Confidence intervals using bootstrap resampling. You can calculate confidence intervals around the estimated performance metrics. Bayesian inference employing Bayesian models. You can obtain posterior distributions for the model parameters and derive uncertainty estimates. Ensemble methods using multiple models trained on different subsets of the data. You can estimate the variability in the predictions. Challenges and fixes. Challenge 1. Overfitting. The model might perform well on the training data but poorly on unseen data. Sample use case. A model trained on a small dataset might memorize the training data and fail to generalize to new instances. Fixes. Regularization. Introduce a penalty for complex models, encouraging simpler models that generalize better. Cross-validation. Use cross-validation to evaluate the model's performance on multiple splits of the data. Early stopping. Monitor the model's performance on a validation set and stop training when performance starts to deteriorate. Feature selection. Remove irrelevant or redundant features that might contribute to overfitting. Challenge 2. Data leakage. Information from the test set might accidentally be used during training, leading to unrealistic performance estimates. Sample use case. If features used for training are derived from the test set, the model might appear to perform better than it actually does. Fixes. Careful feature engineering. Ensure features are created independently of the test set. Data splitting. Split the data into train, validation, and test sets, avoiding any leakage between sets. Challenge 3. Imbalanced data. When classes are unevenly distributed, the model might favor the majority class. Sample use case. In a fraud detection dataset, the number of fraudulent transactions might be much smaller than the number of legitimate transactions. Fixes. Oversampling. Replicate minority class instances. Undersampling. Reduce the number of majority class instances. Weighted sampling. Assign different weights to different classes during training. Challenge 4. High variance. The model's performance might vary significantly across different folds of the cross-validation. Sample use case. A model with a complex structure might be sensitive to small changes in the data, leading to unstable performance. Fixes. Regularization. Introduce a penalty for complex models, reducing the model's variance. Ensemble methods combine multiple models to reduce the variance and improve the overall stability of the prediction. Challenge 5. Poor choice of hyperparameters. Selecting inappropriate hyperparameters can lead to suboptimal performance. Sample use case. Using a default hyperparameter setting for a model might not be suitable for specific data. Fixes. Grid search. Exhaustively search over a range of hyperparameter values to find the best combination. Random search. Randomly sample hyperparameters from a specified distribution. Bayesian optimization. Use Bayesian methods to efficiently explore the hyperparameter space.